Okay, folks, let's take a look at these integrals, right? So the first one, we have the double integral radical y sine y dy dx, right? And we have that over the region that is given in terms of the limits on the integral. So the limits on the integral can be used to induce what the region looks like, right? So if we have the y integral here going from x squared, right, as a lower function, and then one as an upper function, then we have something, in this parabolic region here. But then if we look at the x integral, x only goes from 0 to 1. So now we're only talking about the right side of that region, right? So, our patch of grass, as it were, right, is going to be that region there, right? This is the x-axis, this is the y-axis, right? And we have a lower function of x squared, and that's y is equal to x squared, and an upper function y is 1, right? And then x goes from 0 to 1, okay? All right. Well, the instruction on this integral were to change the order of integration because if we tried to integrate radical y times sine of y, well, we'd be kind of stuck. We can't use a u substitution, and we can't use integration by parts. You should try if you want. At any rate, so in order to change the order of integration, well, this involves changing the way the region is described. Right now, we have this region described as type 1, right? Where, this is up and this is down. And, the proverbial tree grows upwards like that, right? Okay. But anyway, if we're going to change the order of integration, then we can't, consider this to be up and down. We have to look at the world from the point of view of the y-axis, right? So if you want a tree, growing, the tree is going to go upward. So this is going to be up and that's going to be down. Now, previously, we have y is equal to x squared, right? Y is equal to x squared. Well, if you want to solve for x in terms of y, then all we have to do is take the square root of both sides, and we get x is equal to radical y, right? We have x equals radical y. Now, this is the upper function, right, because it's the sky and this is the ground, and the lower function is x equals 0. And then we have, instead of x going between two numbers, we have y going between the numbers 0 and 1. Right? This was previously the function y equals 1. Now it's just the number y equals 1. Okay, so so now we can just rewrite the integral, keeping in mind what x does and what y does, right? Now, if we change the order, that means x is going to go first and y is going to go second. So we look at the region, we say, aha, x is going from a function of 0 to a function of radical y, right? And then y is going between the numbers 0 and 1, right? Now, this is not only possible, it's actually trivial, right? Because as far as x is concerned, anything having to do with y is a number, right? It's like integrating 5 with respect to x would be 5x. So if we do the inner integral, so 0 to radical y of radical y sine of y dx, right? Again, this is a number. So we have radical y sine of y x, where x goes from 0 to radical y. Well, when we plug in x is equal to radical y, look what we get. Nice things, right? We get rad y times rad y, which is just y. So when we plug in radical y, we have y times sine of y. And then when we plug in x equals 0, using the fundamental theorem, we don't subtract anything from, what we obtained in the previous step. All right? So we have y sine y. Perfect. That's the inside integral. All right? So, all right. So now, we go back to the integral. Let's leave it. Let's go I, right? So now I is simply equal to the integral from 0 to 1 of y times sine of y dy. Well, that integral is, not bad, but you have to use integration by parts, right? So to use integration by parts, because see, that's how we integrate a product. It's the reverse of the product rule, right? So in order to do that, to carry this out, we have to pick u to be something and dv to be something. Well, u is going to be equal to y in this case, right? Because when we take the derivative, even though it's in differential form, the derivative of y is 1. So we get 1 dy. dv being sine y dy, all right, we integrate that. We get integral of sine is negative cosine. Okay, good. So, now everything fits, in our integration by parts formula. And, it's going to be, the answer is going to be uv minus integral v du, but I just sort of, crisscross this, right? So I have uv, which is negative y times cosine y, minus the integral of cosine y dy, right? Between 0 and 1, because we have the product, minus the product of cosine y with dy, and we integrate that, okay? All right, well, the integral of cosine is just sine, right? Oh, by the way, this gets evaluated between 0 and 1, right? So what do we have, as our answer? Well, we'll plug in the 1 and 0 and see. So we have negative y times cosine y between 0 and 1. And then we have the integral of cosine, which is sine evaluated between 0 and 1. Okay? Perfect. So what does all that equal? Well, if I plug a 1 in here, I get negative 1 cosine 1, right? So that's negative cosine of 1. And then minus a minus, 0, so that doesn't contribute anything. And then, likewise over here, we have sine of 1, positive sine of 1, okay, minus sine of 0, which is 0. And this is our answer, okay? Minus cosine of 1 plus sine of 1. Okay, great. All right, so let's see what we got going on next. Well, the next thing, we're going to find, the volume of something, right? We're going to find the volume of the function 2xy. That's the tent, right? dy dx. And it's going to be over the unit disk, but only the portion that's in the first quadrant, right? So that's all we want. We want a quarter of the disk. All right, so this is best done using polar coordinates, right? Recall x is equal to r cosine theta, y is equal to r sine of theta, okay? And so we can put that in when we compute the integrand, right? But, let's go in order. We have to rewrite the region, the integrand, and the differential elements, right? All right, so doing so, let's see what we got. Well, the region is really nice, right? R is just going to go from 0 to 1, right? For that, quarter of the circle of radius 1. And theta just goes from 0 to 90 degrees, pi over 2. For the integrand, we have 2 times r cosine of theta times r sine of theta, right? This gives us x and y. And then the differential element, as usual, is r dr d theta. Okay. All right. So let's do the interior integral, right? So what is the interior integral? Well, if we collect, all the r's together, we have 3 of them, right? So we have 2 times the integral from 0 to 1 of r cubed, and that's sine of theta, cosine of theta. Of course, it doesn't really matter what order we write them in because it's multiplication, right? And this gives us r to the 4th over 4. But if we multiply that by 2, we got r to the 4th over 2. Okay, and sine of theta, cosine theta, goes along as constants, and r goes from 0 to 1, right? Well, when r is 0, that's nothing, so we just get 1/2, right? So the interior integral is just 1/2 sine of theta cosine of theta. Okay, perfect. Right. So let's press on forward. Right. So we have 1/2. Actually, I'm going to write this up here because we have to do a few other things here. All right. So the volume is now equal to the integral from 0 to pi over 2. Right. We have a 1/2 which came outside, and then we have sine of theta cosine of theta d theta. All right, well, perhaps the most straightforward way of doing this integral is to use a u substitution with u equal to sine of theta. And then, if we do our little feasibility test, right, I choose u to be sine theta. I choose u to be sine theta. Well, the derivative is just floating around nearby, right? The derivative du then is cosine of theta d theta. What luck! This is du here, and this is u. So in u land, we have the integral 1/2 between somewhere and somewhere, because the u numbers will change, but I'm not gonna do that. I'm just gonna go back to theta land and then plug in the numbers. So I have u du, right? That's all there is to it. Well, the integral of u to the 1, right? We add 1 to the exponent, divide by the new exponent, which gives us 1/4 u squared, right? Between somewhere and somewhere. It's a definite integral. Now, is the passport to u land. So u happens to be equal to sine. So this becomes 1/4 sine squared of theta between 0 and pi over 2. Okay. Well, sine squared of theta means sine theta squared. So when we plug in a pi over 2, sine of pi over 2, sine of 90 degrees is 1. 1 squared is 1. So we get 1/4. All right. But then when we plug in a 0, sine of 0 is 0. So the answer just comes out to be 1/4. Okay. Okay, great. All right. So let's see what's next. All right. So we're going to evaluate now. We have a triple integral, so we're going to evaluate this integral. Uh, well, the integrand is 6xy, all right, and where we have the generic volume differential element dv. Could be dz, dy, dx, or whatever. But we need to look at the region E, right, which is a solid, so we have a triple integral over a solid. And, like I said, a nice way to think about that is, kind of like a temperature function, right? So we have a temperature function over a solid. What's solid? Well, the solid in this case is E, and it's a set of all x, y, and z. Let's see if you can see that far. Sort of, right? Such that, let's say, so z goes between 0 and x plus y, right? Y goes between 0 and 2x, and then x goes between 0 and 1. I think those are the bounds, right? Yeah. Okay. So yeah, so this integral makes sense then if we use dz, dy, and dx. All right. So, given these values here, I'll erase it because I need the space, right? So we have the triple integral. So 0 to x plus y, that's what z does. So we have 6xy, and that's what z does. And then what does y do? Well, y goes from 0 to 2x. And then what does x do? X goes from 0 to 1. All right, so this is pretty algorithmic, right? Step-by-step procedure. We just do each one of the integrals in pieces. So we have the integral of 6xy dz, where z goes between 0 and x plus y. Well, this is equal to 6xyz, where z goes between 0 and x plus y. And then we substitute x plus y in for z, and let's see what we get. We get 6xy times x plus y, right? So, distributing that 6xy, we get 6x squared y plus 6xy squared. Okay? Fantastic. All right, so that's the innermost integral produces this. Okay, well, now that we have that, let's start working our way outwards. So we have the integral from 0 to 2x, right, of 6x squared y plus 6xy squared dy, right? So now we have a y integral. Well, so we add 1 to the exponent, divide by the new exponent. So the new exponent being 2, we divide 6 by 2, so we get 3x squared y squared. Then when we add 1 to the exponent here and divide by the new exponent, now we're dividing by 3, so we get 2xy cubed. Okay? All right. Well, now we have to substitute for y 0 and 2x. Well, the 0 isn't going to contribute anything. Let's see what happens when we substitute in 2x. Well, if I substitute in 2x there, I get 4x squared, right? So I get 3x squared times 4x squared plus 2x times y cubed with the 2x plugged in. So what is that? That's 8x cubed, all right? So that's 16x to the fourth, and this is 12x to the fourth. Well, that just gives us 28x to the fourth, right? 16 plus 12 is 28, 28x to the fourth. Well, that's not too bad at all, right? So when we do, and this is the next, step along the journey, right? So the only thing we have left to do is the integral of 28x to the fourth, okay? And that's an x integral. Well, that being an x integral, again, we add 1 to the exponent, divide by the new exponent, we get 28 over 5, x to the fifth, between 0 and 1, just gives us 28 over 5. We're done. Cool. Good. All right, let's see what we're up to next. All right. So we have another triple integral. All right. So let's see what we have now. Integral number 4. We had the triple integral, okay, of x cubed and dv, the generic volume differential element. And let's see, so this takes place under the cone. I just have to look where we are here. Yeah, okay, so we have this is a particularly strange looking solid, right? So we have a cone that looks like this, but that cone is trapped inside of a cylinder, right? So here's a cone, right? And here's the cylinder which envelops the cone. So this is the surface of the cone. But that's not the region that we're interested in. We're interested in this dotted region under the cone, but above the circle, x squared plus y squared equals 1, right? This is a circle, x squared plus y squared equals 1. But without a circle, which is embedded in three-dimensional space, without any restriction on z, is a cylinder, okay? So we have the intersection of the cylinder with the cone, and here's the cone. Z is equal to the square root of x squared plus y squared, right? So if we were going to write this, well, I think I will write this in, I'll write it I'll write it like so, right? So the integral is the triple integral is of x cubed, right? And if we look at this polka dotted region here, that region has a ceiling of z is equal to the square root of x squared plus y squared, and a floor of 0. Yes, it's bounded by x squared plus y squared equals 1, but this is, if we're looking at just the roof and the floor, right? This happens to be, the x squared plus y squared equals 1. That's going to give us the boundary, the patch of grass over which this roof and floor occurs. But the floor is z equals 0. Okay. So z is equal to the square root of x squared plus y squared, and the floor is equal 0. Okay, well, now let's consider the patch of grass. Well, the patch of grass is just a disk of radius 1. So, I'll use my usual shorthand notation to indicate that. So, we're going to start off with a z integral, but, shortly after that, and yeah, we'll call this dx dy dx. But as soon as we take care of this integral, then it's going to be off to polar land. All right. But we just have to deal with this roof and the floor. That's a z integral. All right. Well, the z integral of x cubed being a constant as far as z is concerned, is just going to be, I'll just do the results of the inside integral, right? So that's x cubed z, where z goes between 0 and the square root of x squared plus y squared. Okay, so we have x cubed times the square root of x squared plus y squared. And that's the innermost integral. That's the result of the innermost integral. Yeah, we have minus 0, but that doesn't change anything. Okay, so let's see what we have. Let's take stock of where we are, right? Now we have our integral I becomes the double integral over the interior of the unit disk, right? And we're stuck with this, x cubed, and then the square root of x squared plus y squared, dy dx. All right? Well, as usual, well, now look, we have two reasons to go to polar land. One reason is that, the disk is, easily described, as a polar region, right? And the integrand is not too much fun to deal with either, right? But when we go to polar land, right, we have x is equal to r cosine theta, y is equal to r sine of theta, all right? And recall that if we had x squared plus y squared, well, that's going to be equal to r squared. So we're going to have an r squared right there. All right, so let's see what this integral I becomes in polar land. So we have the double integral. We can deal with the easiness of the region or the patch of grass. So that's r just going from 0 to 1 and theta going from 0 to 2 pi, right? But we have something a little bit more complicated in here, right? So we have r cubed cosine cubed of theta, just cosine cubed of theta, all right? Then we have, that takes care of the x cubed. Then we have the square root of r squared. Well, that's just r. And then we have the differential element, r dr d theta. Okay? All right, there we are in polar land. Well, I like it when the easy stuff goes first, right? And that's what's going to happen. We'll just have a bunch of r's. We'll have 5 r's, right? R to the 5th. So we have, for the inside integral, which is 0 to 1, we have r to the 5th, and then cosine cubed of theta dr. Okay? We're just doing the r integral. Well, that gives us 1/6 r, well, right over here, equals 1/6 r to the 6th, and then cosine cubed of theta, where r goes from 0 to 1. Implementing those, putting those numbers in, then we just have 1/6 cosine cubed of theta. And that is going to be the result of the innermost integral in polar coordinates. So we only have one thing left to do. Well, one small thing left to do. So we have the integral 1/6 of cosine cubed of theta d theta, where theta goes from 0 to 5. Okay? Now, cosine cubed of theta, looks kind of like cosine of theta, right? But the curves are a little bit different, right? But nevertheless, we're going to have, the area is all going to cancel each other out, and the integral is going to be 0. But that's not a legit argument. So let's pursue a legit argument. Well, all right. So if we want to integrate this, whenever you have an odd power of sine of cosine, or sine or cosine, you're in luck, right? Because we can extract out the odd power, which is just 1, cosine to the 1. We're going to save that to be du, right? In upcoming u substitution. Well, if we're going to let cosine be the derivative, right, then cosine is the derivative of somebody. That somebody is sine. So what I need to do is write cosine squared in terms of sine. But that's easy to do, right? Because cosine squared of theta plus sine squared of theta is equal to 1. Thus, cosine squared of theta is equal to 1 minus sine squared of theta. So we can replace cosine squared of theta with 1 minus sine squared of theta. Let's go ahead and do that. So we have 1/6 outside, right? And then we have 0 to 2 pi. And we have 1 minus sine squared of theta. Then we have cosine of theta d theta. Cool. Now, you remember what I said. If we're going to save cosine for the du of somebody, right, the derivative of somebody, that somebody has to be sine. So sometimes, students will make a mistake and let u be equal to 1 minus sine squared. That's not going to work because we don't have the derivative of 1 minus sine squared. But we do have the derivative of sine, right? So in u land, we'll let u be equal to sine of theta. Thus, du is equal to cosine theta, as we, had planned, right? And so this integral is 1/6 between somewhere and somewhere of just 1 minus u squared du. Well, computing this integral, we get 1/6, and we get the integral of 1 in u land is u. The integral of u squared is add 1 to the exponent and divide by the new exponent, right, between somewhere and somewhere. Well, those somewheres will become 0 and 2 pi as soon as we substitute, for what u was originally in the substitution, right? Well, u was sine, okay? So this integral then is going to be the value of this integral after we compute it is going to be 1/6 sine of theta minus 1/3 sine cubed of theta between 0 and 2 pi. All right, well, now this is really easy to evaluate, right? Because sine of 2 pi is 0. Thus, sine of 2 pi cubed is 0. And then when we substitute in zeros, we get 0 again. So the answer is 0. And that's integral number 4. Okay. All right. So what do we have next? Ooh, I almost messed this up, right? Okay. So yeah. So the last integral we have is an integral which we do in spherical coordinates, right? And so what is that integral going to be? So we have the triple integral, okay, of the square root x squared plus y squared plus z squared, right? And using the generic, a differential element for volume, dv, all right? And this takes place over some, solid q. And let's see what that solid looks like. Well, that solid's kind of nice, right? So that solid's an ice cream cone. So, basically what it is a sphere that's, that's truncated, right? So we have a sphere, but we only go down, part of the way, right? And so what is our sphere? Well, our sphere is we have x squared plus y squared plus z squared is equal to 8, right? That's our sphere. That's the end of our sphere, right? And the cone which cuts that off is z is equal to the square root of x squared plus y squared. Now we don't have to fiddle with these things and set them equal to each other to find a description of the region. We just have to think, in spherical coordinates. Well, in spherical coordinates, right, we have rho, theta, and phi. Well, let's start with rho, okay? Rho is equal to x squared plus y squared plus z squared. I showed that that was true, when I introduced spherical coordinates, right? And which are, by the way, x is equal to rho sine phi cosine theta, y is equal to rho sine phi sine theta, and z is equal to rho cos phi, right? So that's spherical coordinates. We also have to worry about, a differential element, but I'll get to that in a second, right? So, if you want to, prove this for yourselves, just square both sides and you'll get, a double application of sine squared plus cos squared equals 1, right? And you'll see that x squared plus y squared plus z squared equals rho squared. So, back to describing this thing, right? Well, so the outer edge of the cone, right, is a sphere. And that sphere is x squared plus y squared plus z squared equals 8. In other words, rho squared equals 8. Well, if rho squared is equal to 8, that implies that rho is equal to radical 8. Okay? So when we describe this ice cream cone, rho is going to go from 0 all the way up to radical 8. Okay, that's cool. But we're not letting rho go from 0 to radical 8 all over the place, because then we get the whole sphere, right? We only have some of the sphere. Well, let's see, what do we have? Well, another thing that we notice is that if we have the North Pole, right, that's when phi is equal to 0. Well, if z is equal to radical x squared plus y squared, right, that's going to be a 45-degree tilt. And you can see that if you look in the, x y plane, or the xz plane or the yz plane, right? If we look in the xz plane, right? So that we get that by letting y be equal to 0. Well, if y is equal to 0, then z is equal to the square root of x squared. But the square root of x squared is the absolute value of x, which is just a v, and it's a v with slope 1. Well, if v is slope 1, then it tilts down by 45 degrees. So, all right, so we're almost there then, right? We know that rho goes from 0 up to the square root of 8. We know that phi goes from 0 to 45 degrees, pi over 4. Now let's look at this ice cream cone in terms of theta, right? So theta is 0 on the positive x-axis, and then theta starts to go around. Well, if we, want this whole ice cream cone, we don't want to chop it in half or something, then we're going to let theta go from 0 to 2 pi, right? So theta goes from 0 to 2 pi, okay? All right, so we have the description of the region, right? Remember 3 things: the description of the region, the integrand, and the differential element. Okay, all right, so we're working our way there, right? So this integral then in spherical coordinates, it doesn't look like we have to replace x or y, with their values, that I gave, just before on the right-hand side, because all we have is x squared plus y squared is z squared, and we know that that's the square root of rho squared, which is just rho. All right, so, well, let me go over here. So computing this integral in spherical coordinates, we have the square root of rho squared, that gives me rho, okay? As we just said, rho is going to go from 0 to radical 8. Phi is going to go from 0 to pi over 4. So let's put that. So d rho, where rho goes from 0 to radical 8. D phi goes from 0 to 45 degrees. And theta goes from 0 to 2 pi, right? Now, the only thing left is the differential element, right? Well, I gave you that, and it's something you should just ought to memorize, and that's equal to rho squared sine phi. Okay. And now we have the integral in a sensible way that makes computation much, much easier. Okay, so the inside integral is just the integral, is the row integral from 0 to radical 8, right? And what do we have? How many rows do we have? We have rho cubed and then sine of phi, right? And that's d rho. Okay, well, that's just a power function. So we add 1 to the exponent, divide by the new exponent. And then we go from 0 to rad 8, and we have a sine of phi left over as a constant. Well, rho to the fourth, if rho is radical 8, that's rad 8, rad 8, rad 8, rad 8, right? That's 8 and 8, another 8, so that's 64. And 64 divided by 4 is 16. So all we have here is 16 sine of theta. And this becomes, so 16 sine of phi. 16 sine of phi is the result of the innermost integral. All right, so let's go back to, the integral. So now, we've chopped it down by 1. So now we only have 2 integrals, right? 0 to 2 pi and 0 to pi over 4, right? And 16, we can put 16 right outside of the integral. And then we have sine of phi, where phi goes between 0 and 45 degrees. All right, so let's do that integral, right? I'll scrap paper. So the integral of sine of phi, I'll do that over here. Okay, so the integral of sine of phi, so 0 to pi over 4 of sine of phi. Okay, well, the integral of sine of phi is equal to negative cosine of phi, right? So we have negative cosine of phi between 0 and 45 degrees, right? So that's negative cosine of 45 degrees, and that's negative 1 over rad 2, minus a minus cosine of 0, which is 1. Writing that as a single fraction and changing the order there, we can have rad 2 minus 1 over rad 2. And that's the result of the innermost integral, when we have, this reduced to a double integral, right? So, this is gone. I don't need this anymore, right? And now we have that the whole integral is equal to 16 times rad 2 minus 1 over rad 2. And then finally, the integral from 0 to 2 pi of d theta, 1 in theta land, which is just theta. So we have theta between 0 and 2 pi, which of course is just equal to 2 pi. So we'll put a 2 pi outside of that whole mess. And doing so, we have 32 pi times the quantity radical 2 minus 1 over radical 2. Okay? Well, if a radical in the denominator, offends you, then we could, do what they do in high school, and we can multiply by rad 2 over rad 2. In doing so, we have 2 on the bottom, right? Well, 2 on the bottom cancels with 32 to give us 16. So we have finally 16 pi, and then if I distribute this rad 2, I just get 2 minus rad 2, and that is the answer to our integral. All right, so that's that. Okay. All right, so good luck, and I'll see you soon.